So today I will start a new method. It's not a new topic, but a new method called virtual work method. This method will be used to calculate deflection. Just a reminder, we learned before what is the meaning of deflection. If you have a beam and this beam is supported, this beam under the effect of load, whatever the shape of the load, we can expect deformation of this beam. This deformation means this point, for example, will move down by distance called y, which is deflection. And we can expect this point on this new curve will have a tangent. This tangent will have a slope angle or rotation theta with the horizontal. This theta can be called rotation or can be called slope theta. We learned last week a topic or a method called double integration method. This method will help us to figure out what is the value of theta, what is the value of deflection. Today, we will start another method called virtual work method. Just a hint, the method that we learned last week are used or is used for beams only. 99% for beams only. If we have truss, we will use virtual work method. But before doing truss, I will do it for beams. So the new method, virtual work method, nothing new. It will calculate what is the value of theta, what is the value of deflection y at any point. But different technique, different method called virtual work method. Before starting this method, I would like to explain bending moment diagram. I know we covered this before, bending moment diagram, but I would like you to be familiar how to draw moment diagram in a second. So please pay attention to me. Pay attention to me. If you have beam simply supported, means between the roller and the hinge, and you have concentrated load P, the bending moment diagram will be triangle. The vertex of the triangle under the location of the load, like this. And this value of moment will be P A B divide L. I'm sorry. The applied load time this distance divide the total distance L. One more time. If you have simply supported beam, means beam between hinge and roller, and you have concentrated load anywhere, and this distance A, this distance B, and the whole distance is L. The bending moment diagram, you can keep it in your mind forever. The bending moment diagram will be triangle. The vertex of the triangle underneath the location of the load. And here is the triangle. This value of the triangle or this maximum moment value will be P, the load, time distance A, time distance B, divide the total distance L. Any question? For example, if you have beam with length 10 feet and you have concentrated load 20 kip at midpoint. At midpoint means this distance will be 5, this distance will be 5. So Anybody can tell me what is the shape of the bending moment diagram? Yes, I can. The shape of the bending moment diagram in this case will be triangle. The vertex of the triangle at mid-span underneath the load. Here is the triangle. Can you tell me what is the value of this moment? Yes, I can. The value of P, 20 kip, time distance A, 5 feet, time distance B, 5 feet, divide the total distance 10, your value will be 50 kib foot. Any question? Piece of cake. Piece of cake. If you have simply supported beam between hinge and roller, and you have uniform distributed load with value W, the bending moment diagram will be parabola, second order parabola. Second order parabola. This value of the moment will be W L square divide 8. W is the applied distributed load. L is the total length of the beam. For example, if you have beam with length 8 feet and you have uniform distributed load, the value is 2 kib per foot, your bending moment diagram looks like this. Parabola, concave up. This value of moment will be W L square divide 8. The value of W is 2. L8 square divide 8. WL square divide 8. So your value will be 16. So this value will be 16. Please, all of these cases, keep it in your mind forever if you can. Forever as engineer. Any question so far? If you have any question at any time, please let me know. If you have simply supported beam between hinge and roller, and you have concentrated moment at the end of the beam, whatever, the end, at the hinge or the roller, whatever, the bending moment diagram will be value here, M, 0 there, and you have this triangle. First of all, your value of moment will be at the location where your concentrated moment is. The value is down or up based on where is the head of this triangle. Here is the head. Here is the tail of the moment. So wherever the head, we will have your value. For example, if you have moment like this, M, so your bending moment diagram will be 0 on the other side, and you will have M here, and you will have triangle like this. If you have beam and the applied moment like this, you will have 0 at this end, and we will have M at this side, and you have triangle like this. You will ask me, hey, why this triangle is up, which is positive, why this triangle is down, which is negative? Based on where is the head of the arrow. If the head goes up, your value will be up. If the arrow of the head, if the head of the arrow goes down, so I will put my value down. Keep in your mind, if you have simply supported beam like this and your moment is here, be careful. Your value at the location of the moment. In this case, your value will be here, up, because the head is up, and we have 0 there, we have triangle like this. So please keep in your mind, if you have simply supported beam, and we have concentrated moment at one end, so we have triangle. the value of the triangle will be at the location of the moment and 0 on the other side. Your value will be negative or positive based on the head of the arrow. Any question so far? Guys, any question so far? Please, everybody, tell me your feedback. Do you have any question? Do you have any question so far? So I will give you a permission during the exam. You can print or you can copy these cases in a different paper, or I will give it to you during the exam. That's fine. So if you cannot remember all of these cases, it's okay. You can open your note during the exam to figure out these cases. I don't mind. Okay? Okay. The second case. So the first one, I'm talking about beam between hinge and roller. But the second case, I will repeat everything, but we have cantilever. Beam fixed from one side only. So if you have concentrated load P, this concentrated load P time this distance L will make moment and the triangle like this. This value of the triangle equal P time distance L. For example, if you have cantilever fixed here and this load equal 5 kip and this distance equal 4 feet, your bending moment diagram will be, just to keep you updated, this load time this distance would like to rotate like this. So the head of the arrow is down. So we have value down here equal P time L, which is 20. And this one will be 0. So we will have triangle like this. That means if you have concentrated load like this, 5 kip, and this distance equal 4 feet, the bending moment diagram will be, keep in your mind, this load times this distance would like to rotate like this. So the head of the arrow is up. Your value here will be up. 5 times 4 is 20. Your triangle will be like this. That makes sense? I think. The second case, if you have fixed with cantilever and uniform distributed load, your bending moment diagram will be triangle, but I will add parabola. This triangle will have here a value W L square divide 2. So your value here was PL, P times L. In this case, W L square divide 2. And this value of the parabola will be W L square divide 8, like this one. And this is the length L for this beam. For example, if you have cantilever fixed from one side and you have uniform distributed load equal 4 kip per foot and this distance equal 10 feet. Do you know what is the shape of the moment? Yes, I know. Your moment will be triangle will be down. This triangle will be down, negative. How much here? W L square divide 2. Value of W 4. Value of L square 10 square divide 2. Your value will be 200. And we have a parabola because it's a distributed load. This value of the parabola will be W L square divide 8. W 4. L square 10 square divide 8, whatever the value. So these cases are very important. I believe during your FE exam, you will need all of them. The third case, if you have cantilever fixed from one side and you have concentrated moment. Okay, your moment will be down. Why? At this end, why? Because the head of the arrow is down. And this value will remain constant during the length of the beam. No change. Will be remain constant. For example, if you have fixed from one side and you have concentrated moment like this for kib foot, what is the bending moment diagram? The bending moment diagram will be a value here equal 4 down because the head of the arrow is down, and this value will remain constant. Just to remind you, if this beam is simply supported between hinge and roller for kib foot, no, we have different story. Your value here will be 4. It's okay like this one, but will go to 0. In this case, your value 4 remain constant because this one is cantilever, but this one is simply supported beam, which is the difference between this case and this case. Just to keep in your mind, if the bending moment or the applied moment like this, 4, okay, I will follow where the head of the arrow is up, so your value will be up and remain constant. This one is positive, then this one is negative. That makes sense? So looks good. These cases looks good. Okay, now what will happen if you have simply supported beam between hinge and the roller and you have cantilever? So it's a combination between this case and this case. What will happen? Okay, let's see. If you have concentrated load here, so this concentrated load on this part of the beam looks like this concentrated load on this part of the beam. So I will have triangle PL, like this one, PL, this triangle. And then I will connect between this value and the 0 value. What will happen if you have this beam with concentrated moment? Okay, this moment on this part looks like this moment on this part. So we will have a value here negative, and this value will remain constant for this part only. Once you are done, the last value will be connected to 0. Okay, what will happen if you have uniform distributed load? Okay, the uniform distributed load on this part looks like uniform distributed load on this part of the beam. So I expect we will have triangle W L square divide 2, and I expect parabola, this value WL square divide 8. Once you are done, the last value connect it to 0. That makes sense? That makes sense? So I don't care about this part. My concern is what's going on the cantilever. If you have concentrated load, looks like this. If you have uniform distributed load, looks like this. If you have concentrated moment, looks like this. Any question? Any question? Looks good. Okay, I know you have a question. The question is, what will happen if you have, okay, this beam between hinge and the roller and you have cantilever? Okay, that's good. But we don't have this value only. We don't have this concentrated load only. No, we have this concentrated load besides this distributed load. What should I do? Okay, we will do a method which is very, very, very important called superposition method. Superposition method. Yeah. Keep this method in your mind. Superposition means how many load do you have? 1, 2. Go ahead and assume we have each one alone. I'm sorry. Yeah. Assume your beam with this concentrated load only. And then assume your beam with this uniform load only. If you have another load, okay, go ahead and assume the third load only, and so on. So first one, I assumed we have this one alone. What do you expect? I think this concentrated load on this part looks like triangle P times L. This length is L1. And then I will connect it to 0. Like I did here. Then the second case, we have this beam between hinge and roller, beam between hinge and roller, between hinge and roller, and we have distributed load between the hinge and the roller. So I expect your moment to be parabola, like this case. And your value of the parabola here, which is the maximum value, WL squared divided. So my question is, do you think this load is existing alone? No. Do you think this load is existing alone? No. Both of them exist at the same time. That means we will have this shape beside this shape. That means this bending moment diagram can be called bending moment diagram with the method of superposition. So superposition means go ahead and assume each load exists alone. And go ahead and draw bending moment diagram for this load alone. Go ahead and draw bending moment diagram for this load alone. The final bending moment diagram will be this diagram and this diagram at the same time. Looks good? I can give you example. If you have beam, looks like this. We have here 4 kb foot. We have concentrated load here 10 kb, and these distance are 5 foot, 5 foot, 5 foot. How can I draw bending moment diagram with the method of superposition? Okay, first step, I will assume we have this moment alone. Plus, second step, I will assume we have this concentrated load alone. Do you have any other loads? No. So we have two cases only. Can you tell me what is the bending moment diagram for this case? Yes, I can. The value here will be 4 negative, will remain constant, 4. Then I will connect it to 0. Like this case. Then we have beam between hinge and roller, and we have concentrated load. So I expect my moment will be triangle. And this value of the triangle will be PAB divide L. We will have 10 times 5 times 5 divide 10. My value will be 25. This case looks like this one. But we don't have this one alone. And we don't have this one alone. We have both of them at the same time. So your final conclusion is my bending moment diagram will be like this. This triangle, which is 25, beside this shape, which is 4 and 4. Here is the bending moment diagram with a method called superposition method. Do you have any question? Do you have any question so far? If you have any question, let me know. Virtual work method is the total work done by the applied forces and the internal forces of a mechanical system as it moves through a set of virtual displacement. Okay, we don't need to understand this concept exactly, but steps of solution. We have 4 steps. The first step, we need to draw bending moment diagram due to given load using the method of superposition. Wow. So what I did will be the first step. Whatever the given load, I will draw bending moment diagram with the method superposition. Second step, please keep in your mind. Second step, remove all loads and place a unit load at the point or joint where the desired deflection is to be determined. Or place unit moment. So the first one, place unit load. The second one, place unit moment. The first one, unit load if you would like to get deflection. The second one, place unit moment at the joint where the desired slope, theta. So if you would like to get deflection Y, put unit load, 1 kip or 1 kilonewton. If you would like to get the theta, go ahead and put unit moment. Then go ahead and draw bending moment diagram one more time. So we have 2 diagrams of moment. The first one due to the given load, the second one due to the unit load. Then the fourth step will apply the equation of virtual work. For deflection, you will do integration of moment, the first moment by the second moment, divide EI or theta will be integration for the first moment by the second moment divide EI. Integration by diagrams. How can I do this integration? We are going to use this table, but looks like I confused. Let's do an example and see what's going on. This beam AB, which is hinge and roller, has uniform distributed load 8 kilonewton per meter. We need to determine the slope theta at A and deflection at C using virtual work method. We need to do these steps. This method is very easy. First step, go ahead and draw bending moment diagram due to given load using a method of superposition. My question is, do you think we have many load or only one load? I think it's only one distributed. Can you tell me what is the bending moment diagram for this distributed load? Yes, I can. I believe you have a beam between hinge and roller and you have uniform distributed load. I think you are in this case. So the bending moment diagram will be parabola, and the value here of this parabola will be WL square divide 8. Go ahead and find this value. W times L 8 square divide 8. This value will be 64. This moment can be called M naught. First step is done. I draw bending moment diagram due to the given load using a method of superposition. Second step. Remove all external load. Okay, I removed all the external load. No load. I will start first with theta at A. I will start with theta at A. So after I remove all the external load, I will put unit moment at the joint where the desired slope or rotation is required. I'm looking for theta at A. Okay, go ahead at A, put unit moment. 1 kilonewton meter moment equal 1. You will ask me, hey, why you put this moment at this point A? Because I'm looking for theta at A. The steps said, after you remove the applied load, go ahead and place unit moment at the joint where the desired slope or rotation is required. Can you draw bending moment diagram? Yes, I can. Right now we have beam between hinge and roller, and we have concentrated moment. I think your moment will be, value here will be 1, value here will be 0, and we will have this triangle positive. This moment can be called M1. I think this case looks like this one. You will ask me, hey, why you put this value up? because the head of the arrow is up. Any question so far? One more time. First step, we need to draw bending moment diagram due to the given load. Second step, we need to remove the given load. Remove it. And put 1 unit moment where at the location you are looking for theta. So I put 1 moment with a value unit at A. The third step, go ahead and draw bending moment diagram due to the new moment. The final step, theta at A will be integration of M naught with M1 divide EI dl. Any question? If you have any question, let me know. It's very easy. This method is very easy. How can I do this integration? How can I do integration between the two shapes? 1 over EI is outside. It's a constant. Integration of this parabola by this triangle, I can say area of parabola time coordinate from M1. I'm sorry, what you mean? 1 over EI. What is the area of the parabola? This parabola will be 2/3 8 times 64. If you have rectangle, this length is 8, this height is 64, so the area of this rectangle will be 8 times 64. If you draw a parabola inside this rectangle and you would like to get the area of this parabola, go ahead and multiply the area of the rectangle by 2/3. So this parabola looks like inside a rectangle. The length of the rectangle is 8 meters. The height of the rectangle 64. So the area of rectangle will be 64 times 8. Because it's a parabola, I multiplied it by 2/3. Where is the center point of the parabola? Center point is here. Can you tell me what is the value of moment corresponding to this point? I think this value will be 0.5 because the value here is 1. So I will multiply it by 0.5. Your value will be 2/3 times 8 times 64 times 0.5. Your value will be 176 divided ER. This is the value of theta at A. Any question? Any question? So if you have a parabola with triangle, you can get the area of the parabola 2/3 times area of rectangle. Where is the centroid of the parabola? Go down to find the corresponding value of moment, which is 0.5. Then I can get the integration by graphics. I am done with theta at A. Can you tell me how can I get the deflection at C? Okay, let's repeat this method one more time. First step, we have bending moment M naught due to the given load 64. Second step, I will remove all the given load. I will remove all the given load. This time, I will put unit load at the joint where the desired deflection is required. We are looking for deflection at point C at the midpoint. So at the midpoint, I will put unit load. Then I will draw bending moment diagram due to the unit load. We will have moment looks like this triangle. This value will be PAB divided L. I think this value will be 1 times 8. I'm sorry, 1 times 4 times 4 divide 8 equal to. This is the M1. Deflection at point C will be integration of M naught by M1 divide ER DL. I can divide this parabola to two parts, this part and this part. I will show you a different way to make integration. The half of the parabola and half of this triangle looks like this parabola or this half of parabola with this triangle. So your integration can be used, can use this one by this table. 5 divide 12 M times M bar times L. I can do it here. 1 divide EI. The equation said 512 times this value of moment 64 times this value of moment, which is 2, times this length of L, which is 4. So I integrate this half by this half only, because we have another half, and another half I can multiply it by 2. So your deflection at C will be 5 divide 12 times 64 times 2 times 4 times 2 equal 426.67 divided ER. One of you will say, hey, why the first step we have a parabola and we have this triangle? This one is 1, this one is 64. Why you didn't use this table? Okay, you can. It's okay, you can. Go ahead and divide. So we have this parabola by this trapezoid. We have here this parabola by this trapezoid. So you will use this one. And then you have this half of parabola with this triangle. So I can use this half of parabola by this triangle, which is this one. That makes sense? Let me repeat these steps one more time by this example. Example number 2. One more time. We have cantilever fixed at B, and we have one concentrated load 30 kilonewton. We need to figure out what is the slope theta, what is the deflection y at point A. So theta at A, y at A. First step. Can you tell me what is the bending moment diagram due to given load? Yes, I can. I believe this moment will be like this. This value will be P times L will be 90, negative. This case looks like this case. Okay. Next step. Remove all load. I will start with theta. So I will start with slope at A. I will remove everything. If you would like to get slope at A, I will go to A and put moment 1. That makes sense? Third step, what is the bending moment diagram due to the new load? I think this moment will make here 1, and this one will remain constant, positive. So there is M1. In a very simple word, theta at A equal integration of the moment due to given load by the moment due to unit load divide EI dl. 1 over EI outside. How can I do integration of this triangle by this rectangle? You can use your table. We have triangle by rectangle, so I will use this equation of integration. Have M bar times L. Have M90 negative. The value of moment here positive 1, because this one is M and this one is M bar, or this one is M bar and this one is M. That's fine. Time what? Time L. Your length here is 3. So it's half time M bar time L. L equal 3, M bar equal positive 1, M equal negative 90 and a half. The value will be negative 135 divide ER. Here is the theta at E. That makes sense? Very easy. The next part, we are looking for deflection at E. Just to remind you, here is the M naught. This value is 90, negative. I will remove everything, and we are looking for deflection. We are looking for deflection. So I will put at A unit load, not unit moment. If you are looking for theta, I will put unit moment. If you are looking for deflection, I will put unit load. Then go ahead and draw the bending moment diagram. I believe your moment looks like this triangle, negative also. This value will be 3. P times L will give you 3. This one is M1. So deflection at A will be integration of M naught by M1 divide EI dl. 1 over EI outside. So right now we have this triangle, which is negative, by this triangle, which is negative. Do you have in your table of integration triangle with triangle? Yes, we have this one by this one. So I'm going to use this equation. 1/3 M times M times L. 1/3 this M negative 90 times this M negative 3 times this length 3 meters. So it's 1/3 times M times M times L. Your value will be positive, I think. Will be 270 divide ER. This is the deflection at point E. Any question? Guys, do you have any question? I have question. And if you answer this question correctly, I will give you 5 points in the coming exam. So pay attention to me. I will ask a question. And if you answer this question correctly, I will give you 5 points in the coming exam. For this problem, I found slope at point A equal negative 135 divide EI. Anybody can tell me what is the meaning of negative? This value in radian, rotation. Anybody can tell me theta at A equal negative 135 divide EI. Anybody can tell me what does it mean of negative sign? No? No. Benjamin, I'm talking about rotation. Your answer related to deflection, below or above. Above or below x-axis means deflection, moving. But right now I'm talking about rotation. So rotation means clockwise or anti-clockwise or counterclockwise. So your answer doesn't make any sense to me. Marcus, Benjamin, Jennifer, Miguel, I'm so sorry. Your answer is not correct. Guys, positive or negative answer means you assumed correct or wrong direction. I'm sorry? What you mean? Negative 135 means opposite to your assumption. So what did you assume? Guys, in the second step, I removed all loads and I put the unit moment like this. I'm sorry. you put your moment clockwise. I'm so sorry. My value is negative. This direction is opposite to this assumption. Because nobody of you asked me this question. Hey, Dr. Ayman, why, when you remove the all load and you put here moment, why you didn't do like this? Why you did it like this? Both of them should work. Yes, both of them should work. And based on your assumption, like this or like this, you have to wait for your value. If your value is negative, I'm sorry, you assumed wrong direction. Nothing will be changed. But I assumed it clockwise. I'm so sorry. I'm so sorry. This direction is wrong. This rotation counterclockwise. One more time. What is the meaning of deflection of y a equal positive 270 divide ei? Positive does not mean up or down, does not mean above or below. Positive means when you remove the all loads, you are at point A and you put unit load going to down. And your value is positive, both of them matching. So your point will move down, following your assumption. Because one of you will say, hey, when you removed the applied load, why you didn't put the unit load like this? Why you put the unit load like this? Which one will work? Both of them works. This one or this one, whatever. And then I have to wait for my value. If your value is positive, this value will follow your assumed direction. I assumed the unit load going down and your value is positive, this point will move down. That makes sense? We have a different technique for science, not like double integration. Just to remind you, for double integration that I covered last week, I told you if y is positive, it will move up. If y is negative, it will move down. For theta, if the value is positive, I think it's clockwise, probably. The value is negative, it will be counterclockwise. No, we have a different technique in this method. If your value is positive, will follow the direction you assumed. If your value is negative, it will be opposite to your assumed direction. That makes sense?